Hello. Today we're going to learn about transverse shear stress. When we apply shear forces to a body, it generates within that body transverse shear stress, tau, where the transverse shear stress, tau, is equal to the value, the magnitude of the shear force, times a geometric term Q, divided by the second moment of inertia times the thickness of the cross-section. Now, some key things to note about transverse shear stress is that it is maximum at the neutral axes, so maximum at the kind of the centroid of our cross section, and it falls to zero at the free edges, which is the opposite of what we normally see in normal bending stress, right? Now, in finding transverse shear stress, probably the harder thing that we need to do is understand this geometric term Q and figure out how to calculate it. So the geometric term Q, if we're looking at our cross-section, if we're looking down on our cross-section, Q is equal to the integral from y1, which is the lower edge from our point of interest, to C, which is the outer surface of our geometry, over a differential area. The integral of that times y over a differential area. If we were to perform this integral, what we end up finding is that Q is actually equal to the centroid of the area above our point of interest times the area above our point of interest. So if our point of interest, if we want to calculate the transverse shear stress along this line in our geometry, we have to find the centroid of the area above that line and the value of the area above that line, right? If we can do that, then we'll actually be able to find the transverse shear stress. So with this in mind, this Q term can actually help us understand how shear stress develops along our cross section. For example, if we choose the outer edge of our geometry, then the area above that edge is zero. The Q value ends up being zero, and since Q is in the numerator for tau, our transverse shear stress is equal to zero. So that just enforces that if we're on the top edge or the bottom edge, if we're on the edge where there is no area above our point of interest, shear stress is equal to zero. Now, what if we choose a point directly in the center of our beam? Well, if we choose a point in the center of our beam, then the area above that point is maximized. And if the area is maximized, Q is maximized, and thus our maximum transverse shear stress is located at the center of our cross section. And these 2 points, the center and the edge, give us the bounds of shear stress. So between the free edge and the center of our member, our transverse shear stress is ranging between those 2 extremes. Now let's do an example of solving for the maximum shear stress for a given shape, a given cross section. Let's start with a rectangle, and let's say that rectangle has been subjected to an applied shear force of V, and we want to find the maximum shear stress. Well, we know it should be at the neutral axes, or the center of this cross section, and so let's go ahead and go about calculating it. If our line of interest, our point of interest, is the center, then we want to find the centroid of the area above that line, as well as the actual value of the area itself. Let's assume the rectangle has a cross section of a width B and a height H. Based on that, we can find its centroid should be 1/4 of the height, and its area should be its thickness times half of the height. If we put those 2 together, we find the geometric term is equal to thickness times the height squared divided by 8. We also can use our appendix to find that the second moment of inertia for a rectangle is the thickness times the height cubed divided by 12. With Q and the second moment of inertia found, we can put them together to find our maximum shear stress for a rectangle, where with a little bit of math and a little exercise, we find that the maximum shear stress is equal to 3 times the shear force divided by 2 times the cross-sectional area. Now this here is the closed form solution, the exact solution for a rectangle. So given any rectangular cross-section, we can just directly use this equation. But there are other geometries where we might want to find the maximum transverse shear stress. So in our book, in table 3.2, we have some examples for like circular cross sections and triangular cross sections. But also in our appendix A19, we have solutions for like T-beams and I-beams and other types of interesting beam shapes. So we don't always, 90% of the time, we don't have to go and try to derive the solution from first principles. Instead, we can use these tables, get our max value, and then start to try to solve our problems. Now, in some cases, when we don't have a simple geometry or the geometry isn't given in our appendix, we may have what we can call a composite shape. The composite shape is basically where we have some simple geometries that form something that is more complex, a composite geometry. With normal bending stress, we've found that we had to apply the parallel axes theorem in order to find the second moment of inertia that was appropriate for the composite shape. Similarly, we have to do something to find our geometric term for a composite shape. And that is that we need to sum for each of the areas involved the location of their centroids and the value of those areas. So for example, say we have a T-beam and we want to find the Q value. Well, the T-beam, and we want to find it from, we want to find the maximum transverse shear stress, which is the centroid of the overall T-beam. Well, then we have an area from this member, and we have an area from the second member, and each of them have their own centroids. So if we sum the centroid times the area of each of these together, then we end up with our composite Q term. It's important to note that we also have to apply the parallel axes theorem to get that composite second moment of inertia. With these terms calculated and noting how transverse shear stress evolves, we can very easily solve for the maximum transverse shear stress in a member.